A spider drops from the ceiling corner of your bathroom, and your entire body reacts before your brain even catches up. Heart rate spikes, skin crawls. You grab a shoe or a glass, whichever is closer. It's barely the size of a coin. But the real answer is far stranger than a coin-sized spider, because 300 million years ago, that same instinctive fear would have been justified. Terrifyingly justified. There was a time when insects and their relatives grew to the size of dinner plates, house cats, and in one case, a fully grown human being lying down. You are not afraid of bugs by accident. Your nervous system inherited that flinch from ancestors who lived alongside creatures your modern brain has no reference point for. Picture a dragonfly with a wingspan wider than your arm span, gliding silently between towering ferns. Picture a millipede longer than a canoe, armored and segmented, dragging itself across a swamp floor with an audible scrape. Picture scorpions the size of dogs. This wasn't science fiction. This was the Carboniferous period, roughly 300 to 360 million years ago, and the fossil record from this era reads less like paleontology and more like a monster catalog. So why doesn't the world look like that anymore? Why can a spider the size of your palm feel like an outlier, when creatures that size used to be background noise? For decades, one theory dominated the conversation, and it comes down to something invisible, something you're breathing right now without a second thought. Oxygen. Insects don't breathe the way you do. You have lungs, a heart, and blood that carries oxygen actively through your entire body under pressure. An insect has none of that. Instead, insects rely on a passive network of tiny tubes called tracheae, threading directly through their bodies, delivering oxygen straight to tissues through simple diffusion. No pump, no pressure system, just oxygen slowly seeping inward through a maze of tiny pipes. Here's the catch built into that design. Diffusion only works efficiently over short distances. The bigger an insect's body gets, the longer those internal pipes have to stretch, and the harder it becomes for oxygen to reach the center of the body before it's needed. In today's atmosphere, this puts a hard ceiling on how large an insect can physically grow. Push past that ceiling, and the innermost tissues simply suffocate. But atmospheric oxygen hasn't always been fixed at today's 21%. Geochemist Robert Berner spent decades reconstructing ancient atmospheres using long-term carbon cycle models, piecing together indirect evidence buried in rock layers, fossil charcoal, and ocean sediment chemistry. His reconstructions pointed to something remarkable about the Carboniferous period specifically. Atmospheric oxygen levels weren't sitting at 21%. They were closer to 35%, some of the highest concentrations in the planet's entire history. That extra oxygen wasn't a minor difference. It fundamentally changed the math of diffusion. With that much more oxygen available in the air, it could push further into a body before running out, effectively raising the size ceiling for any creature relying on passive tracheal breathing. Suddenly, a millipede could grow to over 2 meters long. A dragonfly relative called Meganura could stretch its wings past 70 centimeters tip to tip. The insects weren't doing anything unusual for their era. They were simply built to the maximum size their atmosphere allowed, the same way modern insects are quietly capped by ours. This idea sat as a compelling correlation for years. High oxygen era, giant bugs, seemingly obvious cause and effect. But correlation in the fossil record is cheap. Actually testing the mechanism required something the Carboniferous period couldn't provide: a controlled experiment. That's exactly what physiologist John Harrison set out to do, working alongside researcher Alexander Kaiser in the early 2000s. Instead of digging through 300-million-year-old rock, they built sealed chambers filled with artificially enriched, oxygen-heavy atmospheres, recreating something closer to Carboniferous air in a modern laboratory. Then they raised living insects inside them across multiple generations, dragonflies among them, and simply measured what happened. The insects grew larger, not dramatically overnight, and not into house cat-sized monsters after a single generation, but measurably, reliably larger than insects raised in ordinary present-day air. Harrison and Kaiser had done something the fossil record alone never could. They turned a historical correlation into a demonstrated, testable mechanism, atmosphere directly shaping body size, replicated in real time inside a lab. Here's the twist that makes this genuinely strange to sit with. It means the size of a creature isn't purely a product of its genes, its evolutionary lineage, or how many millions of years it's had to grow. For an entire category of life on Earth, size is a direct negotiation with the chemistry of the air itself. Change the atmosphere, and you change the physical limits of an entire body plan, instantly, without a single mutation required. And the atmosphere did eventually change, dramatically, and it wasn't external. It was the swamps themselves. The Carboniferous period gets its name from carbon, specifically the immense forests of primitive trees and plants that dominated the landscape, growing in vast humid swamps for tens of millions of years. When these plants died, the fungi and bacteria capable of efficiently breaking down their tough woody material hadn't fully evolved yet. Instead of decomposing and releasing their carbon back into the atmosphere the way dead plant matter does today, that vegetation piled up layer after layer, undecomposed, eventually compressing into the massive coal seams that still power parts of the world today. Every time you've heard the phrase coal age, this is what it refers to. All that buried, undecayed carbon meant enormous quantities of oxygen, a byproduct of the very photosynthesis that built those forests, stayed in the atmosphere instead of getting reabsorbed. The high oxygen levels weren't a fluke. They were the direct exhaust of an ecosystem that had, quite literally, learned to grow faster than the planet could recycle it. Eventually, fungi evolved the enzymes needed to break down that tough plant material efficiently. Decomposition caught up. Oxygen levels slowly settled back down towards something resembling today's atmosphere. And as the air thinned, out of oxygen's reach, the giants shrank with it, generation after generation, following the same diffusion math in reverse, until insects settled into roughly the size range you recognize today. This is where it should genuinely unsettle you a little. The ceiling on insect size right now, the reason nothing in your garden approaches dinner plate proportions, isn't really about biology refusing to build anything bigger. It's about the air itself refusing to allow it. Change the atmosphere enough in either direction and the ceiling moves with it. It happened once already, driven entirely by plants outrunning the decomposers meant to break them down. Think about that the next time you find yourself in a heavily air-conditioned office building, or reading about rising carbon dioxide levels, or wondering whether ecosystems are more fragile than they look. The Carboniferous giants are proof that something as invisible and unremarkable as a shift in gas concentration can quietly rewrite the maximum size of an entire category of animal life on Earth. No predator, no evolutionary pressure, no mutation required. Just chemistry, patiently pressing on biology until biology has no choice but to comply. So the next time a spider drops from the ceiling and your whole body flinches before you've consciously registered why, remember what that flinch is really responding to. Not the spider in front of you, the one your ancestors' ancestors actually had reason to fear, breathing air so rich it could have built something the size of a dinner plate, and did. The more we learn about the past, the better we understand ourselves. If this video sparked your curiosity, don't forget to like, subscribe, and follow Phoenix Primeval for more fascinating stories from history, science, and human evolution. Thanks for watching.